All right. Good evening, everyone. I am evenvalue, as you might be knowing me on Discord and Codeforces and everywhere else. And in today's lecture, I will be teaching you guys about segment trees. So let's get started with that. So segment trees are like these OP data structures that you can have in your arsenal while solving problems. And it's so segment trees can not only be used to solve hard problems, but you can also sometimes use it to overkill some of the easy problems. So sometimes you can reduce a easy problem to some very standard thing that you can solve using segment trees, which can also be solved using some simpler techniques, but you can just directly segment tree bash it and solve it. So yeah, so segment trees are like super useful data structures, and they appear quite often in both Codeforces contests and OI problems as well. So it's super useful to learn them. And it's also personally one of my favorite data structures. So yeah, all right. With that said, let's get started now. So before we start talking about segment tree in particular, let's talk about something that you guys did in the previous class, right? You guys learned about prefix sums from Krishnakant. So what you do in prefix sums is essentially you're given a static array. Now I'm using the term static over here. We will come to what that means in a moment. Uh, I'll just take a random array here. Okay. And we can store the prefix sum of this array, which looks like this. Did I mess something up? 2, 7, 11, 14, 15, 21. Yeah, okay, I think this is correct. Um, all right. So here we can answer queries of the type, give me the sum from index, I'll just index them as well. So give me the sum of all the elements from index, I don't know, 2 to 5, let's say. So if I want the sum of all the elements from 2 to 5, then what we can do is we can say that it's going to be the sum up till prefix of 5 minus prefix of L minus 1, which happens to be 2 minus 1, which is 1. So we can say it's going to become 15 minus 2 equal to 30, right? This is what we do in prefix sums, right? Does that make sense to everyone? All right, cool. So now we can answer a lot of these L2R sum queries, and we can answer each of these in order 1 after this initial pre-calculation, initial order n pre-calculation. Okay, we pre-calculate our prefix array, and after we pre-calculate our prefix array, we can answer these L2R queries in order 1. Yeah, so far so good. Okay, so this is only if this array is static. Now, when I say static, I mean constant. So this array is not changing. But if I try to change the array values, so say I also give you updates. Now updates can look like update the position I, index I, to some value v. So for instance, if I say update the position value at position 3 to, so I'll say I equal to 3, update it to value v is equals to, I don't know, we can say 5. So when I do that, we essentially look at the array, we look at the position 3, which is initially 4, right? And we now say it's going to be changed to 5. Okay. And the result of this is quite impactful on like the prefix array, because all these values, the 11, 14, 15, 21, all of these values will change now. Okay. And in fact, uh, so all of those values are going to change. So we are going to have a new prefix array, prefix sum, that we need to recalculate, right? So it's going to become like this now. Okay. And as you can see, all of these values changed, right? So every time I give you this update operation, perform an update on index I and change its value to V, we can make sure the entire prefix sum changes by updating something that is closer to the first element. Okay, and then the entire prefix sum changes from that moment on. So if we try and recalculate a prefix sum, it's going to take us order n time per update, which is quite bad. Yeah. So we can essentially, this prefix sum idea, this allows us to perform updates in order of n, worst case, and queries we can perform. Queries are basically the L to R sum query. We can perform those in order 1. So does this make sense? Okay. So this, although this works, this is quite slow, because assume some case, some scenario where I give you a lot of updates and very few queries. Then your overall code will be quite slow, right? And if such a thing happens, what you can do is you can instead do somewhat like a brute force, right? Where you can manually update. Okay, I'll just take another array and then we can do that. So let's say my array, I'll again have some random values. Is this the same now? Okay, I don't think it is. All right. So what we can do is I'll again have two types of queries. One is the update and one is the query that I'm going to ask. Okay. Now every time I update, I will manually change the array value at that index to the new updated value. So in the sense that if I now change, let's say, the value at position, let's say, I don't know, let's say position 1 itself. If I change it to 6, then I will get this new array and I can just manually change it. So this is going to be order 1. Okay. And now every time I query, what I can do is I can iterate from the position L. So let's say I want to query the sum from 2 to 5. Then I can iterate over all indices from 2 to 5 manually, and I can sum them all up. Okay. And this is going to take order n time worst case, because I can query index 1 to n each time. Right. So we can also do this. Does this make sense? Um, all right. So I see a couple of thumbs ups. All right. So I'll assume that you guys understood this. So we have these two different kinds of solutions to this. One is going to perform updates in order n and queries in order 1, and the other is going to perform updates in order 1 and queries in order n. So in case you have a lot more updates as compared to queries, you will use the second solution. In case you have a lot more queries as compared to updates, you will use the first solution. Okay. But the problem arises when we are approximately having an equal number of updates and queries, and both of them are a huge number. In that case, order n is going to be quite slow for us, right? And we want to kind of look at something better. And this is where segment trees come into the picture. Okay, this is how segment trees come into the picture. And we will now talk about how exactly do segment trees work. And we'll also look at the implementation. And then we'll also look at the different kinds of problems where segment trees will help us to solve. Okay. So let's get started with the segment trees now and look at how segment tree will help us solve this particular problem. Okay. So, all right. So I'll just paste this down there. Okay, cool. So let's take an array of size 8. So let's say my array is 5, 1, 4, 6, 2, 8, 7, 3. Okay. Hopefully this has 8 elements. Yeah, I think it does. So what we do is we are essentially having this tree-like structure. I hope you guys know what a tree is, right? So this is a tree. This is a binary tree, to be more precise, with 8 leaves. So each node in the tree has either no children or it has 2 children. Okay, and we have kept 8 children in particular, 8 leaves in particular, because each array value is going to be associated with 1 leaf. Okay, so we are essentially creating a binary tree with n leaves. So that's what we are trying to do here. Okay, so I will just fill in the numbers here as is. Okay, and now I hope these edges are kind of visible as well over here. So what these edges essentially mean is you take the sum of the two values below you. Okay, so like this node, for instance, will be the sum of this plus the sum of this, right? So it's going to become 6. And similarly here, it's going to be the sum of these two values, which is 10. Okay, and I'll keep doing this. Okay, so this is what we get. This seems wrong, right? 1 second. Yeah, this is 36. Okay, so over here, I will now try and be more specific. This value 5 to 5 is from index 1 to index 1. This is covering the sum of all the values from index 2 to index 2. This is covering the sum of all the values from 3 to 3, 4 to 4, 5 to 5, 6 to 6, 7 to 7, and 8 to 8. Now, because this node is the sum of this and this, the range that it covers is 7 to 8. The range that this covers is 5 to 6. The range that this covers is 3 to 4. And the range that this covers is 1 to 2. And I'll also do these for the above nodes. This is 1 to 4, 5 to 8, and 1 to 8. So does the entire tree structure make sense over here? How exactly did we make the tree? We'll come to that slightly later. But whatever tree I've made, does that tree make sense? And do you understand what these ranges essentially imply? So I hope everything so far is clear. And in case you have any doubts, then you can send them in the chat. Okay, I'll take it as you don't have any doubts. Okay, so all right, now let's actually come to how we build the tree. How exactly am I building the tree? So first of all, I have my root node, which is going to have this 1 to 8 range. Okay, my root node is going to cover the 1 to 8 range. So its left child, okay, if you notice the left child is going to cover half of whatever the root covered. So it's going to cover 1 to 4, the first half, and the right child is going to cover the second half. Okay, and we are going to make them cover the 1 to 4 is length 4, 5 to 8 is also length 4, right? It's covering 4 elements. So we'll try to split it as evenly as possible between the left child and right child, and that's how we are representing my tree. Okay, so root covers 1 to 8. The left child gets the first half, which is 1 to 4. The right child gets the second half, which is 5 to 8. The first child of this node will get the range 1 to 2. The right child will get the second half, which is 3 to 4, and so on. So that's how we are deciding what ranges they get. And over here, the split was nice every time because I took a power of 2, right? A to the power of 2. We will look at what happens in case the split is not so even in later on, right? But currently, this is how we built the tree. We took the range of the root, we split the first half to the left child, and we gave the second half to the right child, and then we recursively did this until we were only remaining with one range, like 1 to 1, something like this, and that those were the leaves. Okay. So does the segment tree, the entire structure, does that make sense to you guys? All right, excellent. So now, how is this useful? The first useful property about this tree that I just built is its height. Okay, what is its height going to be? So height is going to be some function of the number of leaves. So let's say the number of leaves I have is n. Okay, so I have n leaves over here. Then can you guys tell me what the approximate, like the function height is going to be? Yes, so Yemen Lander said log n. Samvar said log n. Yes, so it's going to be log n. Now, can somebody tell me why it's going to be log n? So it's going to become log base 2 of n. But can someone tell me why it's going to be log base 2 of n? Because every time we divide the number of leaves into two parts, then continue, does h count the root? Yes, so okay. Height is essentially, think about height as the distance from the root to a leaf. So over here, it's like 3. Number of edges that you traverse. Uh, you can think of that as the height. Yemen Lander said because every time we divide the number of leaves into two parts, then continue. Um, we divide it into two parts, but that doesn't quite prove why it's log n. Okay, the real proof of why it's log n is that's actually a very common proof with such kinds of structures. It is that you start off with the leaf, any leaf you want, okay, and every time you go up, right, every time you go up by one level, your size doubles. So size is the range size that you're covering. So over here, the size was simply 1. Now, if you go up one level, then the size becomes 2. It doubles. Okay. And when you go up again, it will double again. So it will be like 4 now. And if you go up again, it is now 8, the size. Right? And since the root node has size n, you essentially only need to make approximately log n uh, going up movements before it essentially reaches uh, n, the root, and that is why the height becomes log n. So does that make sense to you guys? Okay, so Samba said yeah. Anybody else? Okay, so no doubts. Okay, so I hope everybody clearly understands that this is going to be approximately log n, right? It's going to be around the like log n plus 1, log n minus 1, log n, something like that, right? It's approximately going to be log n. And that is a very useful property to have. Why? We will look at that soon. Okay. So actually, let's look at it right now. So let's say I update, let's say I perform an update. Okay. So I say update position number, let's take 3 to some value 9. So this is I. So I is 3 and value is 9. Okay. Now let's look at what is going to happen. Now when I update this value, firstly, let's look at the nodes which get impacted by this change, the values which get impacted by this change. So firstly, I'll use blue for this. Firstly, this gets impacted. this will also get impacted, this will also get impacted, and this will get impacted. Okay, and none of the other values, none of the other nodes will get impacted apart from the ones that are colored. Doesn't everybody understand why? Yeah, it's because none of the other ranges contain the index 3. So these are the only nodes which contain the index 3. And since those were the only indices that took the sum of 3 into account, the value of 3 into account, those are the only nodes that are going to change. For instance, all of these are from 1 to 2, they are not impacted. All of these values, they are from 4 to 8, so these are not impacted. Okay, only the values that are colored in blue over here, only those are impacted by this update. Okay, so how many nodes are there? How many impacted nodes are there? Like how many blue nodes were there that I colored? Log n. Yeah. So it's going to be approximately again height plus 1 to be more precise, but it's going to be again order of height, which is order log n. So only log n nodes I have to change, and more precisely, I need to change um, the index 3 itself, its ancestors as well. So 3 and all of its ancestors. Only those values are going to change. None of the other values are going to change. And I hope that makes sense to everybody, right? Okay. So what is the value at index 3 going to become? It's going to become 9. At 3 to 4, what is that value going to become? It's going to become the sum of the two children that it has, which is 15. And what is 1 to 4 going to become? It's going to become the sum of, again, the two children that it has, 6 plus 15, so that is 21. And finally, 1 to 8, the root, it's going to have some 41, 21 plus 20, right? So this is how we perform updates. And the time complexity for updates is what? We just discussed that. What is the time complexity for updates going to become? Log n, right? It's going to become log n because only the ancestors of the node that we updated, the leaf that we updated, only those are going to change. And since the number of ancestors is bounded by log n, we can say that the overall update time complexity is going to be log n as well, right? Did everybody understand that? I hope that was clear. All right, all right. So that was updates, and that is how height was useful for updates, right? So that is why we need to split this as evenly as possible. You know, the 1 to 8, we need to split it into 1 by 4 comma 5 by 8, because 1 to 4 1 to 4 and 5 to 8, because if we don't, then this order log n height property is not going to be maintained. Okay, so that is why the height property is like super important. All right, so let's move on to the next thing, which is queries. All right, so let's talk about queries now. um, so queries are slightly more complicated. They are not as easy to explain as updates, but we'll figure it out now. Okay, so what is going to happen in queries? So let's say I am given a query. Let's take 2 to 7. Okay, so I want the sum of all the elements from 2 to 7. All right, so what exactly is going to happen over here? Okay, so first I come to the root. Okay, I come to the root and I say, all right, root, I am interested in the sum of the values, the indices 2 to 7. Okay, now the root checks, okay, is 2 to 7 am I completely a part of 2 to 7? So it says, is 1 to 8 a subset? um, is it a subset of uh, 2 to 7? It checks this, and it is not, right? It is not. So what it does is it gives it says, okay, query both my children, query the left child as well and query the right child as well with the 2 to 7 range that you're interested in. Okay. So now over here it says, okay, I'm interested in 2 to 7. Over here as well, it says I'm interested in 2 to 7. Now 1 to 4 sees this. 1 to 4 is like, okay, am I a complete subset of you? Am I a complete subset of 2 to 7? Okay. And if it is, then it will return immediately. But in this case, it is not. So what it will do is it will send again, it will query both of its children individually. Okay. So again, this says I'm interested in 2 to 7. I'm interested in 2 to 7. Okay. And now things get interesting over here because 3 to 4 is completely lying inside 2 to 7. Right? 3 to 4 completely is a part of 2 to 7. So it will immediately return whatever sum it had. So it returns 15 over here. So I'll take red color maybe. It will return 15. So does everything so far make sense? All right. So what we do next is, okay, so this returned, my right child over here, this returned. Let's now talk about this. This again says, okay, I'm interested in the sum of everything from 2 to 7. It says that, okay, 1 to 1 is completely not lying in 2 to 7. So I'm not interested in 1 to 1 at all. So it will not go to the left child, it will only go to the right child. And it will say, okay, I'm querying the all the nodes, like I'm querying the sum of all the elements from 2 to 7. Are you a complete subset of 2 to 7? And here 2 will say yes, I am a complete subset of 2 to 7. So it will immediately return whatever value it had. So it will return 1. Okay. And this will return whatever it got. So it will return 1 as well. And this overall returns 16, like 1 plus 16, right? That's what the left child returns, the left child of the root. Now let's do the same thing on the right child. The right child is going to then query, because 5 to 8 is not a complete subset of 2 to 7. It is then going to query both of its children, right? It's going to query 5 to 6 and 7 to 8. It's going to query those, and it so we're going to query 2 to 7 on the left child here and on the right child. The left child sees this and it's like, okay, 5 to 6 is completely inside 2 to 7, right? So whatever, I don't need to go further down because you're completely interested in my value, right? So I will just return whatever I have, whatever value I have, which is 10. Now the right child over here, this 7 to 8, it looks at this and it's like, okay, no, my complete range does not is not a subset of 2 to 7. So then it will go to the children and it will only go to the left child because the right child it's not interested in at all. So like 8 is completely not a part of 8 to 8 is not a part of 2 to 7 at all. So it will not go to the right child. It will only go to the left child and it will check whatever this value it has. So 7 to 7 and it has value 7 as well. And it's like, okay, is 7 to 7 a subset of 2 to 7? And you say yes, it is a subset of 2 to 7. So then this will immediately return 7 itself. Okay, and so this returns 7, and so this overall returns 17. Okay, and now this will sum up both of these to return 33, right? So does that make sense to everyone? Now this might have been a little bit confusing, so in case you have any doubts, then please feel free to ask. Anybody? So I saw somebody raising a hand temporarily over there. I think it was Pranav. So do you have any doubts? What if the number of elements is odd? That is a good question. I will come to that slightly later. If the number of elements is odd, then we will figure out what to do. But for now, let's work with the simpler case of even because it is easier to explain, right? And once we figure out how the even case works, we'll come to odd, right? Yeah. So, all right. So far, so good, I suppose. But now we answer the more complicated question about what is the time complexity of this. Okay. Now, this is not so easy to calculate or like notice the moment you see this problem. But this also turns out to be order log n. Okay. And the reason for that is consider some node. Okay. And you get a query from the left part. Okay. Like your parent. So let's say you're the left child of your parent, and it sends you an LR query. Okay. Then you have two options. Okay. Either LR is a part of both of your children. So like let's say this child is this node is, let's say X, let's say this node is Y, let's say this node is Z. Okay. And let's say this is from LY to ZY. Sorry, LY to RY, from LZ to RZ, and this is from LX to RX. Okay. And you've gotten a query L to R. Okay. Now LX, RX, all of these values is basically the ranges that they cover. So for instance, this node will have L to be 8 and R to be 8 as well. This node will have L to be 5, R to be 8, and so on. That's what LX and RX are. Okay. So let's say the um, query that you get is from the parent, and you're the left child of that parent. Okay, and you get the query. So then you have two cases, really. Either, okay, you have three cases, let's assume. Either you return immediately because your LX and RX is a complete subset of LR. In that sense, in that way, you will completely return whatever query you got. Or you go to both the left child and the right child, or you only go to the right child. Okay. Now, why can't you only go to the left child? Mm, um, okay, let's actually think about this a little more. So actually, how do I prove this without being saying some complicated stuff? Let's say. Okay. Okay. So let's say I'm interested in whatever is the sum from this to this, okay, from this leaf to this leaf. Now, what is going to happen is you're over here initially. You're like, okay, I need to query both my left child and my right child. So you go to both of them. Then you go to both this guy's left child and right child, this guy's left child and right child as well. And then you go to this right child. But over here, you don't go further down. Okay, you don't go further down because you're completely interested in this. So this will immediately return. This will also immediately return. And this person will further go down to the right child only, sorry, left child only, and this is how it's going to happen. This will then return, this will then return, and this will then return, like this, like this, like this, and this. Okay, that's what's going to happen. Now, the thing is over here, if you notice, each level, by the way, I'll come to you in a moment somewhere. Okay, you're essentially marking at most 4 nodes. So essentially in this level, you're only marking one node. When I say marking, I essentially mean visiting. You're visiting only these 2 nodes in this level. In this level, you're visiting 4 nodes, all 4 nodes. And in this level, you're only visiting 2 nodes. Okay. Now my claim is you are going to only visit at most 4 nodes per level. Okay. And you're going to visit at most 4 nodes, and your chain, you're going to go down from at most 2 nodes. Okay, so in this case, you're going down from this node and this node. You're going down from this node and this node. You're going down from this node. So each level you're going to go down from at most 2 nodes, and you are going to visit at most 4 nodes per level. Okay, and the reason for that, you can think about this intuitively, is think about this as your leftmost chain. Okay, so then you eventually go to the leftmost child that you're interested in, and think about this chain as your R. Okay, this is your rightmost chain in the segment tree. Now every time, so let's assume you keep going left, 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 left. Okay, like this, and then you go right over here. You keep going right, and there'll be some point where you'll go left and everything. But this is the general structure. Okay, this is the left child. This is the path to the left child. This is the path to the right child. Not right child and left child. Sorry, my bad. The path to the left endpoint that you're interested in, L endpoint, L leaf, and the R leaf. Okay. Now, whenever you go down over here, if you try going down from this to this will immediately return, right? Because you're going to be interested in the entire subtree of this anyway, because it's going to be to the left of L and to the right of R. So you're going to immediately return over here. If you come over here, again, it's going to immediately return because whatever subtree is going to be a part of it is completely going to lie inside L2R. Okay, so you're only going to essentially visit all the nodes on the left chain, this left chain that you're going to have, and this right chain, and maybe their children as well. That's all whom you're going to be visiting, right? And the total number of these nodes is going to be order log n itself. It's going to be more precisely order 4 times log n, which is order log n. Okay. Now this was probably complicated. So did everybody understand? And also Sambar, what was your doubt?
Yeah, so my doubt was that, so my doubt was that from this, would you be able to figure out for like a segment, a generalized segment tree, what is the worst case, like what is the worst range L to R they can give, which would take the most amount of time, like which would cause you to visit the most number of nodes?
Yeah, that's going to be, I think, 2 and n minus 1. So if you query 2 and
Okay.
n minus 1, we're going to essentially visit. So this is a very small segment tree, so it's hard to describe this. But if you query 2 to n minus 1 over here, you're forced to visit 4 nodes per level, usually. Okay. And except for like the first 2 levels and the last level, you're going to visit 4 per level. And that's like the worst case that you can achieve. So yeah, so
Okay, I see.
2 to n minus 1 is going to be the worst case, of course. But even that is going to be only visiting a total of 4 times log n 4h nodes, which is going to be order log n. Okay. Now this proof was a little hand wavy. So did people understand this? Okay, I got 1 thumbs up. Other people? Okay, so is anybody having any doubts though? As to like, did anybody not understand why it's uh you know not log n or something? Okay, Aditya Raj Chopra, uh doubts?
Um, why are we visiting 4 nodes per like level?
Okay, that's okay, so I'll try explaining that once more. So by the way, you get the part that, so we have the left leaf, L leaf over here, and we have the right leaf over here. There's going to be some path from the root. Okay, this is the root. Okay. The number of nodes in this entire segment is going to be order log n, and this is also going to be order log n. Okay, this is essentially the height, right? Now, the moment you try to go away from this path, like let's say from here you try to go away to the right child over here, what is going to happen is this entire subtree, that whatever this node covers, is going to be a part of L2R itself, right? So this will immediately return. Okay, so this will immediately return whatever it got. And if you try to do the same from here, if you try to go to the left child over here, then this will again immediately return. Okay, so the worst that you can do is you can visit 4 nodes per level, which is more precisely like you went here, you went here, the left child over here obviously exists as well, and the right child here. So you're visiting at most 4 nodes per level, and these two are going to immediately return. These two are immediately going to return. This will further go down, and this will further go down. But only, and because this will again return, like visit 4 nodes over here, these two will again immediately return, and this will continue downwards. That's what's going to happen. So you're only going to visit at most 4 nodes per level. Did that make sense?
Yeah, thank you.
Okay. So because you're only visiting order log n nodes per query, your overall query time complexity also turns out to be log n. Now, did that make sense to you guys? After the first 1 to n nodes, you will query a prefix or suffix with a range. Yeah, exactly. So yeah, so whatever Abhigna said is exactly right. So over here, actually let's take this as an example. Um, you will so okay, except for the root, if you go to 1 to 4, you're essentially interested in the entire suffix, right? Like 2 to 4 suffix of 1 to 4 node. So you're interested in the 2 to 4 suffix over here, and over here you're interested in the 5 to 7, I think 5 to 7 prefix. So over here you're only interested in the suffix, and over here only interested, sorry, yeah, only interested in the suffix here and only interested in the prefix here. So your suffix, whatever child you go to, one will immediately return. So this will always immediately return, and this will also immediately return, the prefix child that you call. So one will immediately return no matter what you do, and the other will keep going down, right? So this is what will happen. So only one will keep going down no matter what. The rest of the nodes will just return. So one from the left end and one from the right end, those will go down, and all other nodes will immediately return over here. And there are going to be at most 4 nodes that you visit per level. That's what's going to cause order log n time complexity. Okay. So that was for query. I hope that made sense, right? Everyone? Uh, okay, cool. All right. So now let's come to the numbering of nodes. Okay. Now I said that we have these nodes and everything, but I never really talked about uh, how we store the segment tree or how we store all of these nodes, right? So let's talk about that as well now. Okay. So there are different kinds of numberings that people use. Um there is a one very common numbering, and I don't use that numbering. I use a slightly different numbering. So I'll actually we'll have a look at both of them, and then I'll continue teaching with my numbering. But let's first have a look at the common way that people use. Okay, the common way is that you name the root, you give it, you number it 1. Okay, and then you number the left child twice of whatever your value was, your numbering was. So you number this 2. Okay, and you number the right child twice plus 1. So 2 times 1, which is 2, plus 1, which is 3. Okay, so for this, then you number twice of whatever it was, so 4, and this is going to become 4 plus 1 over here. So it's going to become 6 twice of 3, twice of 3 plus 1, which is 7. Twice of 4, which is 8. Twice of 4 plus 1, which is 9. Twice of 5, twice of 5 plus 1, twice of 6, twice of 6 plus 1, twice of 7, and twice of 7 plus 1. That's how the numbering goes. So did that make sense to everyone? Okay. So this is the most common way of numbering a segment tree. The way I use is slightly more complicated, but it offers its own advantages that we will look at slightly later. Okay. So my way of numbering it is, okay, I will give it, first I name the root 0. Then I go and name the subtree of the left child first. And after that, I'll go and name the right subtree, right child subtree. Okay. So I first then name this subtree. Okay. So I'll name this one in the beginning. Then I'll go name the left subtree of this. And after I name the left subtree, I'll name the right subtree. So let's name the left subtree now. That's going to become 2 over here. Again, I'll name the left subtree first and then the right subtree next. So this is going to then become 3. And now I'm done with naming the left subtree. So now let's go to the right subtree and rename and name that. Sorry. So my entire left subtree over here is done. So now let's go to this right subtree. So over here is going to become the next one, which is 5. Then this, which is 6, 7. This entire thing is then done. So I'll go over here and I'll name this 8, 9, 10, 11, 12, 13, 14. So did everybody understand my numbering, my way of numbering the segment tree? Okay. So, okay, I got a couple of thumbs ups. Uh, so, all right. Now let's say, now also each node is going to be associated with the L and R of it, right? So like this is going to be 1 to 8 for the root node. This is going to become 1 to 4. This is going to become 1 to, sorry, 5 to 8 and so on, right? You can also number them. You can also have the ranges for each node, right? So this is how it will look like, the numbering. Now I'll also talk about, I need to talk a little more about numbering, but I'll do that slightly later. Let's now go to the question that I think Pranav asked. Yeah. And what if the elements, number of elements is odd? Let's go to that as well. So, all right. So let's say number of elements that I have is odd, which is, let's just say 5. Okay. So the number of elements is from 1 to 5. Let's say the indexing is from 1 to 5. Then how am I going to build my segment? So over here, what we can do is I can have 2 children for this, right? My left child is going to have from 1 to 3 and 4 to 5. Now, how did I come up with 3 and 4 numbers, right? So then I'll define a variable called mid, which is L plus R by 2 and float. Okay. So what is L? What is R? L and R is the is like 1 and 5 respectively. So over here 1 plus 5 by 2, and they're going to floor that, which is 3. Okay. So we have 3. So what you do is you split the left child. So if your current node was L to R, here is your current node, it's from L to R. Your left child is going to be from L to mid, and your right child is going to be from mid plus 1 to R. Okay, that's how it's going to look like. So over here we determined that mid is 3. So my left child is going to be from 1 to 3, and my right child is going to be from 4 to 5. Okay, and we can recursively do this for both of these children as well. So can somebody tell me the range for this child over here, this node? Yeah, Pranav is correct. It's 1 to 2. All right. And this is going to be from mid plus 1 to R, so 3 to 3. And this is going to be from 4 to 4. By the same logic, this is going to be from 5 to 5. Now the leaves are done, but for all the numbers, all the nodes which are not leaves, they will continue having two children. So it's like this. And this will then have 1 to 1 range, and this will have 2 to 2 range. And that's how your segment tree will look like. Okay. It's slightly, it is not as balanced as what our 8 leaf segment tree was, but this is how your segment tree is going to look like. And let's also talk about the numbering. Okay. The numbering is going to be, again, the root gets the first value, my left child gets the next. Okay, I number my left subtree first, and that's going to be 1 over here, 2 here, 3 here, 4 here, 5 here, 6 here, 7 here, and 8 here. So did the numbering make sense over here? I did basically the same thing as what I did over here. I number the left child first, and then I number the subtree the right child next. Okay. All right. So Samba said yes, it makes sense. All right. So that's how this looks like. And now I will ask one last question before we move on to the implementation of segment tree. And that is, if I have a node X, okay, this is my node X, the value not X, the node's number is X, 5 over here, okay, and its range is from L to R, okay, then I want the index or numbering of the left child and I want the numbering of the right child. So can somebody tell me what this is going to be and what is this going to become? I want a formula for both of these. So did the question make sense to you guys? Yes. So Rishit Narang is correct. The left child is going to become x plus 1. The right is going to be slightly more complicated. So what is the right going to become? And by the way, assume that you also calculated mid. The mid is equals to the same formula that we used, L plus R by 2. So you have these 4 pieces of information available with you. You know what is X, you know what is L, you know what is R, and you know what is mid. So then how would you calculate? Okay, Aditya asks, explain it again. So I'm basically asking that I have my node X over here. Okay, the node's numbering is X, and its range that it covers is from L to R, and its mid is from L plus, and its mid is defined obviously by the same formula that we used over here. Right, it's L plus R by 2 ceiling. Sorry, L plus R by 2 floor. Then I'm asking what is the index or the numbering of my right child. So for instance, the numbering of my left child would become x plus 1, right? Which you can notice from here as well. It's going to become, so this was 0, and the left child's number is going to become 1. If this was 1, left child's number is going to become 2, 1 more than that. So 2 is going to become 3. And 6 is going to become 1 more, so 7, right? So so if your value is x, then your left child's numbering is going to become x plus 1. What is the numbering of the right child now? So if I plug 1 comma 3 and mid equal to 2, if I plug in these 4 values, I want to be able to get 5 as an output. Does that make sense? The question now? Okay. So any ideas, people? Is it x plus 1 plus r minus l plus 1? X plus 1 plus r minus l plus 1. This seems wrong. Okay, fine. Someone answers it as 2 into mid minus l plus 1 plus x. Yeah, this is correct. Yeah, okay. And we will look at the derivation for this now. The reason is because let's go back to the property of segment tree being a binary tree. So whenever you have a binary tree, I'm supposed to draw binary tree, right? Yeah. Let's say I have a binary tree that looks like this. Now this has let's say n leaves. Okay, so in this case it has 4 leaves. Then it totally number of nodes that it totally has is 7, right? So in particular, if a binary tree has n leaves, then how many total nodes does it have? Um, 2 to the power n plus 1, that is wrong. Does 7 appear to be 2 to the power 5 to you? Yes. So Samvar and Rashid are correct. It is 2n minus 1. And this can be inductively seen as well. Basically, if you have n leaves, then in one move you can remove one element, right? That is like what I basically mean is if you have 4 of these leaves, you can remove both of these, 2 of them, and then you can essentially replace it with just the parent, right? So your overall you went from n to n minus 1 with this deletion, and you can keep doing this, and each of these one step essentially represents a new parent. So then you go to n minus 2 and so on up until you reach like 1. Yeah, you reach 1, which is the root, and the total number of steps that you took is going to become n minus 1. So there are n minus 1 total leaves, sorry, total parents, and plus you initially had n leaves, so it's going to become 2n minus 1. So yeah, so that is, so basically if you have any binary tree with n leaves, then you'll have 2n minus 1 nodes totally. And that is what we are going to be using over here, this fact. Let's come back here. So over here, let's talk about the subtree of L. The subtree of L, this had mid, so okay, so this node had the range L to mid, right? So the number of leaves that this child has is how many? How many leaves does the subtree have? Yes, it has mid minus L plus 1, right? So the total number of nodes in this entire subtree is twice of this, twice of mid minus L plus 1, right? So that's the total number of nodes. Uh, so you number all of these, nodes first. So it's going to become uh, plus x, right? Because you add this, right? And after that, it's like that's what is going to be the numbering of this right node, right? Did that make sense? So you number x, you number all the children over here, and then you number this value over here. So its index is going to become this. Yeah, so this is the index of this. Okay. And the reason for using this numbering is actually going to be seen, like what is the advantage that this numbering offers as compared to the other numbering, like this kind of numbering. It's basically that over here, if let's try drawing the segment tree for 6 nodes. I'm going to do this quickly. So if you have 1 to 6, I'll just use byte only. So if you have 1 to 6, you're going to have 2 children, right? This is going to be from 1 to 3 and 4 to 6. Then they want to have two children over here. This is going to be from 1 to 2. This is going to be from 3 to 3. This is going to be from 4 to 5, and this is going to be from 6 to 6. This is going to be from 1 to 1 and 2 to 2. This is going to be from 4 to 4 and 5 to 5, like this. Okay. So over here, if you follow the first kind of numbering, then you're essentially going to get 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to become 12, and this is going to become 13. So if you notice, we missed out 10 and 11, right? But because we are going to be allocating this memory, we are going to be wasting the space that we could have used for something. Like, we are essentially saving up space by using my numbering as compared to this. Over here, your 10 and 11 numbers, those are wasted. Those don't make sense in the segment tree, right? So that's why this offers a better space optimization, this kind of numbering. My thing will not care about this. It will just number them and use a ping for this. My thing will number them like this: 3, 4, 5, 6, 7, 8, 9, 10. So essentially there is no wastage of any memory over here, and that is the only advantage that this offers as compared to the other numbering. So in the first numbering, in the numbering where you name the children 2x and 2x plus 1, over here you will need to allocate 4 in memory if you have n leaves, and over here you don't care about n much. You can always use only 2n minus 1 nodes precisely. So over here it's going to be wasting like 2n nodes approximately, this kind of segment. That is the advantage of this. So did everybody understand? Okay, all right. So all right. So that's the only advantage. So if you want to use this kind of numbering, the first one, if you found that simpler, then you can use the first kind of numbering. But if you want to use my sort of numbering, that works as well. Okay? The only advantage I've already told you is just the memory optimization. Otherwise, there is no other advantage that this offers. Okay. So with that said, let's move on to the implementation for this. Okay. So, all right. Um, Hopefully my second. Yeah. All right. So hopefully my IDE is visible. And by the way, the problem that we discussed is precisely this problem, right? Where you update the value at particular position to certain value, and we want to query the sum of all the values from the range A to B, right? So this is what we are trying to code up now using segment tree. All right. So the first thing that I'll do is I'll make a class for segment tree over here, and let n be the number of leaves that we have. So we have n over. Now we are essentially storing the tree that we had, the segment tree. We are going to be storing that as an array. Okay, and that's what the numbering was for, so that we can store it as an array. Okay. Now I will come to what node is. Node is essentially what is the value that we are storing at every node. So in this problem, we are only storing the sum of a range, which is an integer. So we can just name it int sum. That's the only information that you are storing at this particular node, right? So this is what it's going to be like. And now we can build our segment tree. So let's actually implement build. Um, okay. So over here, X is the index of my current node. L and R are the ranges which this node covers, and A is the leaves that I need to kind of set the values to, the default values of the leaves initially. So over here is going to be given by this array, right? So my first condition is if L equals R, then if L and R are the same, then that means it's a leaf, right? So then I can immediately set AX to, sorry, TX dot sum to AL, and I can return. So did this if condition make sense to everybody? Samvar said okay. Other people? Yemen Lander said yes. Pranav Sanghi raised the hand. So like, okay, what is the doubt, Pranav?
I raised it by mistake. I
Okay,
went to set the thumbs up.
that's all right. That's perfect. Okay, so this if condition was hopefully clear. The next thing that we do is we define what mid is. Mid is L plus R by 2, and by default C++ and most programming languages will take the floor of this, right? So this is the floor of L plus R by 2. So now I can say I build my left child, which is x plus 1, right? That we discussed this already. My left child is x plus 1, and its range is going to be from L to mid, and we can pass my same array A. Okay. Now we are now going to also build my right child. So my right child's index is going to become 2 into mid minus L plus 1 plus x. This again we discussed, right? So we can build my right child and I can pass A, right? Does this make sense to everybody so far? All right. Now this, so the first thing that actually varies from segment tree problem to segment tree problem is what your node is going to become, right? What information do you store at each node? And that is why I made a separate struct for this, because the rest of the segment tree part is going to remain the same. Only this node part changes. The next thing that changes from segment tree problem to segment tree problem is what your unite function is. So I'll come to what I mean by that in a moment. Um, okay, so over here I can then say, all right. So unite is essentially how you're merging the values, how you're using the values of your two children to calculate the parent's value. So if you remember in the segment that we did, we calculated the value of the parent as the sum of the values of the two children. So that is exactly what we're doing here. We are saying that the value of the parent tx is the sum of the two children. So tx plus 1 and ty. And this sum is being done inside the unite function. Okay. So we are uniting the value of the two children to get the value of the parent. That is what I'm saying. And this is the other part that changes from problem to problem. And that is the reason I've not done it here. Because over here, my goal is to make this as templatable as possible so that you remember that this part is going to be fixed no matter what kind of problem you face, right? And the only thing that changed so far are node and unite. Okay, does that make sense to everyone? Okay, so we are done with the build function. So did the build function make sense to everyone? Okay, so next let's do the update function. So this, by the way, builds the segment tree for us. So now I will implement my update function. So my update function is not going to return anything. It's going to take in XLR. So it's going to take in the position P where we need to update, and it's going to take the value V that we need to update it to. Okay. So if L equals R, again this means that it's a leaf. And if it's a leaf, then this is the node that we need to update. This is the leaf that we need to update. Okay. So then I can say over here that tx dot sum is equals to B, and I can return over here. Okay. Again, I will define my two quantities that I defined earlier, mid and y. Okay. Mid is L to mid is my left child's range, mid plus 1 to R is my right child's range, y is the index of my right child, x plus 1 is the index of my left child. Okay. So over here again. So now we need to decide where we need to update now. Do I need to update my left child or do I need to update my right child? Now, when do we update my left child? If the position P, this position P, we update the left child only if P is in the subtree of um, uh, my left child. And when is that going to happen? When L less than equals to P and P less than equals to mid, right? But when I come inside the current node, I'll assume that it is already greater than equal to L. So I'll only update if it's lesser than equal to mid. So did this step make sense? Everyone? Okay. Alright. And otherwise, if I'm not going to the left child, then that means I need to go to the right child, and that is just going to be by mid plus 1 R P P. Okay. Alright. So another advantage, by the way, to using like numbering these variables like this is that the number of lines that you take to call functions is the same. So over here, if you notice that build is this, like this line has the same number of characters as this line. And the advantage is that if you typoed something, if you missed something, then you can immediately catch it. Right? So this is a small bonus to implementing it this way. You can immediately catch bugs in case your second line, like in case if I let's say forget mid plus 1, I just do mid instead. I'll be like, oh wait, these two lines are not the same length, so I probably made a bug, and I can recheck, and I'll be like, okay, I'm supposed to do mid plus 1 over here, right? And the same goes for here as well. These two lines are the exact same character length, which is very nice. All right. So that was update. Actually, not yet. So tx is equal to 9 tx plus 1. After I update my children, I need to update my own value. That is what this is doing. Okay. So I hope that made sense as well. Is update clear to everyone? Okay. All right. So I got a couple of thumbs ups. Uh, so this is how you update. Now let's move on to query. Now query is going to return whatever type that we had stored at each node. So it's going to return a node here, type node. Okay. So query. So we have our indices. So XLR is again the same thing as what was there previously. Now we are going to be querying a range QL to QR. That is what QL and QR stand for. If my current range is a complete subset of QL QR, so if QL less than equals to L and R is less than equals to QR, then I can immediately return, right? This was again what we had discussed. If it's a complete subset, then we can immediately return. And otherwise, what I can do is do this. Okay, this is again the common part in both of the in all of these segment tree functions. So this, very common. And the next thing that you do is you need to make three cases. The first case, okay, is left child only. Second case is right child only, and the third case is both. Okay, so whether you need to go to left child only, go to, go to, and go to, go to. Okay, these are the three cases that you have. Now, when do you go to the left child only? If okay, you go to the left child only if your entire QR, so like QL to QR is going to be taking some segment, right? And again, screen share them. Give me a minute. Okay, so over here we have So my QL to QR is, let's say, this segment over here. This is QL to QR. All right. My segment tree node is, let's say, the left child is from L to mid. This is my L. Let's say this is my mid. Then over here, if QR is before or like less than or equal to mid, what I can say is that you will never want to go to my right child, right? So because this entire range that you're interested in, you're never going to be interested in my right child. So I only go to the left child. Yeah, does that make sense, everyone? Okay, I got one thumbs up. Other people? All right, cool. The second case is only going to my right child. It is going to happen when, so this is again my L to mid for my left child, mid plus 1 to R for my right child. Okay. If QL and QR are like this, okay, essentially if QL is greater than mid, okay, or greater than equal to mid plus 1, then I will never go to my left child, right? So it always only makes sense to me for me to go to my right child, and then that is what I'll do, only go to the right child. And your final case is going to both, which is you are going to do only when neither of these two conditions are satisfied, right? Something like this will happen. QL will be here, QR will be here, right? And this is going to be part of both this and this. Okay, those are the three cases that I need to handle, and I hope the three cases made sense to everyone. Yeah. Okay, all right. So let's come back. So if QR is less than equal to mid, this is my first case. I only go to my left child. Just a second. Sorry, my bad. Yeah, so if it's only going to be in the left child, then what I can do is I can query, I can only return whatever I query from my left child. So x plus 1, L mid, QL, QR. Yeah. Otherwise, if it's only, I need to only go to my right child, then I can do mid less than QL. Then I return query by mid plus 1 R QL. Okay. And otherwise, I need to go to both of my children. So I return whatever I get from querying my left child and whatever I query from my right child. I'll query both, right? So I just unite whatever I get from my left child and whatever I get from my right child. So the unite of those two things, right? And again, the advantage is that both of these are the same lines. So I know I haven't, at least I can be sure that I probably haven't created any obvious bugs. Okay, so these are both the same number. Again, a huge uh, thing that saves you, when you create bugs. So yeah. Did the query part make sense to everyone? Okay, Nishant says yes. Other people? Yemen Lander says yes. All right, excellent. So this was the main implementation of segment tree. I will just do some more specifics about. So I'll just now come here and we can implement whatever is specific to this problem. So int n q c in n q a of n for int or for int and x in a c in x. Then we will be given a lot of queries of this type. So while q minus minus int lr c in lr and also the type, right? So type. and type lr. Okay, so if uh, okay, type 1 is update the position and type 2 is this. So if type equals 1, else, okay, then lr is also not found. So in this case, we need to take in the position p and the value b that we need, right? And I can say I'll also declare my segment tree over here, seg tree st. I can say st dot update. Okay, my root node is 0, which is going to be covering a range from 0 to n minus 1. Okay, and it's going to be from, I need to update position p minus 1 because they are one indexed, I suppose. They're one indexed, right? Yeah, I think they're one indexed. So let's check once to make sure. Yes, so they're one indexed. So that's why p minus 1 and value b. Okay, also with here I need to build my segment tree. So build 0, 0, n minus 1. Okay. Over here lr, cn, lr, and st dot query from 0, 0, n minus 1, l minus 1, r minus 1. Again, minus 1 because of um, one based indexing, and that should hopefully work. Let's check. Okay, apparently it doesn't. Let's see if we make any bugs. Right. Sorry. Just taken a size and t of 2m. Okay, so over here what I do is I just like my t was not initialized, so it was like size 0. So I initialize my t with some size, and I don't need to build over here anymore because I can send build from inside the constructor. Alright, and let's now try running that. But oh, yeah, so 14 to 11 is correct. I'll submit this as well. A slight thing, I need to make this in 64, like long, I think. Uh, that should be the only change, I believe. Yeah, I think that should be the only change. Let's submit. Uh, yeah. Um, all right, good. So we got AC, and that is how you implement segment tree. Um, so did that make sense to everyone? Okay, I got a couple of thumbs ups. All right. So that was the first problem. This is one of the most basic problems that you can get, that you can solve using segment trees. Again, the main part to notice is that from problem to problem, the only thing that changes is what this node is going to be and what the unite function is going to become. Okay, and otherwise most of the other stuff is going to remain the same. Maybe build over here, you might need to change this from problem to problem. Maybe update, you might want to add this, but otherwise the main structure is going to be the same. Okay, query is going to be pretty much the same in all problems, but yeah, this is how it's going to look like. So hopefully that made sense to everyone. Uh, Now my next goal is to solve parentheses checking. So I will explain the problem. Actually, let's just I'll give you a moment to read the problem actually, and I'll then. Can you share your code on Discord or something? I can do that. Yeah, I'll do that after the lecture if that's fine. Or I can also do this, right? I can go here and share code to others. This is like a temporary thing. I'll also share the code on Discord, but yeah. Okay, so let's look at parentheses checking next. Uh, I will give you a minute to read and then I'll explain the problem as well. Okay, so hopefully you guys read the problem. I will go back to sharing my OneNote. All right. So I just copied the first example here. I think the first example only uses the query operation, it doesn't use the update operation, but we can get to that in a moment. Okay, so does everybody know what a balanced bracket sequence is? So a balanced bracket sequence is that you can essentially pair up every open bracket with the corresponding closed bracket in vague terms. Okay, the formal definition will be on the problem statement, but in vague terms, every open bracket should be paired up with some closed bracket like this. Actually, to be fair, it's not like that. It's like, um, okay, it's essentially like a stack. You can keep a stack, okay, and every time you see an open bracket, you push it to the stack, okay, you push it to the stack, and every time you see a closed bracket, you pop from the stack. Okay, so you pop that, and then you see this, then you again pop this. And a balanced bracket sequence is when you can perform all of these operations, in the sense that when you perform a pop operation, the stack should never be empty, right? And in the end, your stack size should be 0. Okay, essentially the stack should be empty. That is what a balanced bracket sequence is going to be like. So for instance, this is a balanced bracket sequence, this is a balanced bracket sequence, um, and something like this is a balanced bracket sequence as well. So this is what a balanced bracket sequence is, and in this problem we are tasked with uh, trying to find whether a range from L to R, whether or not that is a balanced bracket sequence. So in the first query, we have 1 to 4, which is simply this. So is this a balanced bracket sequence? Yes, it is, right? And that is what is the answer to that as well. Next is from 1 to 2. 1 to 2 looks like this. This is not a balanced bracket sequence, right? The stack is not going to be empty in the end. And from 4 to 5, this here you're trying to pop from an empty stack, so this is also not going to be a balanced bracket sequence. Okay, so this is what we have to do. We also have another type of operation that we can perform, that we have to perform, and that is an update. in an update, what we do is we swap the characters onto different positions. So we'll be given I and J. For instance, let's say I swap, say index 2 with index, let's say 5. So if I do that, this and this gets, okay, they're the same characters, my bad. That's not going to affect anything. Let's swap index, let's say 2 and 4 maybe. So if I swap index 2 and 4, this is going to become like that, I think. So now if I query 1 to 4 again, if I do the same 1 to 4 query again, now my string is going to look like this, which is not a balance sequence, bracket sequence. So yeah, so these are two types of operations that I need to be able to handle, and I need to answer, and I need to be able to answer both of these kinds of operations. So how do I do it? So anybody ideas? So in case you have any idea, then let me know in the chat. And by the way, whenever so obviously this is a segment tree problem since we are discussing this in a segment tree lecture. So more precisely what I want to know is what your node is going to look like, right? This is what we discussed in the previous implementation part as well, where I essentially said that the only thing that are going to change from problem to problem are what you're going to be storing at your node, and secondly, what is going to happen to your unite function. Yeah, your unite function, nodes L and R, how we are going to be uniting them. So these are the only things that change from problem to problem. So I'm only interested in what happens to both of these in this problem. I'll give you guys like a minute or so. I can't give you more because of time constraint on the lecture, but hopefully you'll have enough time to kind of at least digest what the problem is trying to ask, and then we can move on to the solution. Okay, so Rishit says that a node can be a Boolean, okay, which is whether or not this is a valid, uh, this entire range, whether or not it's valid. The problem with this, Rohit, is how do you answer, like what is your unite going to become? That's the question. Like what is your unite going to become? Right? So your unite is not going to be simple. In fact, I can also think of a case where it's going to become false, false, and also false here. So this is also false, and these are also individually false. Right? So this is not going to work. Or at least maybe bool is perhaps one thing that you might require to store, but that is not the only thing that you want to store, at least. So yeah. Um, so okay, I will come to the solution, and again, I apologize for not being able to give you guys more time, but the solution is to only store two integers. Okay, which is open and closed. Now, open and closed, these are how many unpaired open brackets are there and how many unpaired closed brackets are there, right? So, for instance, if I take some range, if I take something like, I don't know, this, okay, let's take this, then over here, this bracket is paired with this, okay? But this closed bracket is not paired, and this open bracket is also not paired, right? So, in this case, your int open unpaired thing is going to become 1, and your closed variable, that is also going to become 1 because you have one unpaired closed and you have one unpaired open. So does what a node hold, does that make sense? Okay. So we are only counting the number of unpaired things. So we are not counting these two, for instance. These are already paired, so we don't care about them. Okay? We only care about how many unpaired are there. Now the reason why this is going to be useful is because let's consider my left child. Left child is going to be containing some kind of bracket sequence. My right child is going to be containing some kind of bracket sequence. So let's take this for instance. Actually, let's just take something nice, right? Maybe this and this. Closed, open, closed, closed. Okay, something like this. So can somebody tell me what is going to be the value of open over here? 2. Yep. And what is the value of closed? 0. Yeah. What is the value of open? Sorry, open here. Open is 0. Yeah, that's correct. And what is the value of closed? It is 2. Yeah, perfect. So now when I unite these two, when I merge these two, my string obviously becomes the like concatenation of both of these. So it's going to look like that, right? And what I can basically say is I had, so whatever is merged, I'm going to mark them with a yellow dash. So this is already satisfied. Now over here, this part is already satisfied. I'm basically marking whatever is already satisfied over here. This was already also satisfied. And now over here, these are the new things that are going to be satisfied. So these two opens are going to be satisfied with these two closed, right? And what we can essentially say is the number of things that matched. So match is my left child, how many ever open he had, min of actually, min of however many open my left child had, and however many closed my right child had. Okay, these are now going to match. So over here, both of these were 2. So both of those got matched. Like 2 of the opens got matched with 2 of the closed. So does that make sense? What match means over here? People, does match make sense to you guys? Okay, I got thumbs ups. Okay. So what I can now do is I can now say that, so let's say answer is my uh, how many opens, like answer is what I need to calculate for this node, right? The open and close for this node, I'll call it answer. So answer, how many opens is it going to have? It is going to have whatever opens my left child had minus whatever got matched, okay, plus whatever R also had open, okay, and my answer dot close is going to become whatever my left child had closed plus whatever my right child had closed plus some of my right child's closed got matched, right? So minus match. So this is how many closed, unpaired closed there are. So does this unite make sense to you guys? Um, People? All right. So Pranav said yes. Other people, do you have ideas? Like questions? Okay. So Yeah, so what you can do is you can only have these two variables. Now, when is a range good? When is a range balanced bracket sequence? Do you understand the question? Like when is a so what do the values of open and closed need to be in order for it to be a balanced bracket sequence? Yeah, exactly. So both of those need to be zero. So if both those values, if both open and closed are both zero, that means there are no unpaired closed and no unpaired opens, and that means that this entire thing is a balanced bracket sequence. So yes, that is what you need to do, and the update should be hopefully easy to perform, right? Because for so if a single node is just opened, then its open is equal to 1, close equal to 0 for a leaf. This is, and if it is this, then you can say that its open is 0 and close is 1, right? So you update, so every time you have a swap operation, you can update the two indices individually, and then for the query, you can just query the uh, range from L to R, and you will get open and closed, right? Check if both of those are 0 or not, and if they are, then print yes, this is a balanced bracket sequence, and if it is not, then you print no. So does that make sense to everyone? I will not go over the implementation, by the way. Implementation, I think I've already sent all my implementations on Discord. So if you want to check them, you can check them on Discord. But otherwise, this was the main idea. And I think I already told you that the main things that change from a segment tree problem to a segment tree problem is what this node is going to hold and is what unite is going to become. So that is already that I already explained over here. So try coding this yourself before seeing my implementation. Okay. So with that, this problem is done. I hope there are no questions. If there are, you can either unmute and ask them, or you can send them on chat. That also works. So hopefully the problem solution made sense to you guys. Okay. Let's move on to the next problem. It is hotel queries. I'll again send you the link on the chat. Um, so this is the next problem. Again, I'll give you guys like a minute or two to read, and then we can try and talk about this. Okay, so I hope everybody read the problem. Um, if so, I will again share my OneNote. Okay, everybody read the problem, right? Okay, I'll just explain the problem once as well. So essentially, we are given an integer sequence like this. I'm not going to be, I'm going to try and be as formal as possible here. So like this, and each time what I try and do is I find the first person whose value is greater than equal to the first query. So like first query is 4 here, second query is 4, third query is 7, like that. And this is my initial array. Okay. So if I query 4, I'll try and find the first person whose value is greater than equal to 4. It is this guy, and I'll print his index. So it is 3. And once I print the index, I'll also update that guy. I'll decrease his value by 4. So it's going to now become 0, and I've tackled the first query. The second query, I'll again try and find the first person who is greater than equal to 4, which is going to be this guy, index 5. So I will say I print 5, and I'll also update this. I'll decrease this value by 5, so by 4, my bad. And then I check 7. I check the first value, which is greater than equal to 7. I find none of the values to be greater than equal to 7. So I just print 0. 0 means it did not exist. And then you can do it for 1 as well. 1, both of these will be 3 will get updated to 1 overall. And then you can print the first index itself. So yeah, that's what's going to happen. So hopefully the problem is clear. So is the problem clear? Everyone? Okay, so Pranav said yes. Other people? Rishit, Aditya, all right. Cool. So this is what is happening here. How do we do this? Now this uses a very nice technique called walk on segment tree. But before we come to what is walk on segment tree, you can also solve this using binary search, right? So what you can do is you can store what is the maximum value in a given range. In your segment tree, your unite function, your unite thing is going to be return max of whatever L and R are. So this is what we call a max segment tree, where each node is going to hold the maximum value in its segment. Okay. So if I query some range L to R, it will tell me what the maximum value in this L to R range is going to be. Right? Does this make sense to everyone so far? Okay. So what I can do is I can binary search on the first index which has a value of greater than equal to whatever my query value was. So what I can do is I can do my normal binary search, right? And low, high, you can set them to default values like 0 and n minus 1 if you want, and while, or like n in case it doesn't exist, right? And while low less than equals to high, you do binary search if query from 1 to mid. Okay, if this value was greater than equals to whatever my query value, then you can say that your value lies on the left half from low to mid, and otherwise it lies from mid to high. Right, you can do the normal binary search, and using binary search you get the index which you need to update. Right, so does that make sense to everyone? And then you can perform the update manually, like what we discussed. You do the normal update in the segment, right? So did this make sense to everyone, what I mean by binary search? In case somebody did not understand, I can always repeat it. Okay, so Aditya asked me to please repeat. So okay, Aditya, what I'm basically doing is, okay, these values are actually kind of nice. So we'll take initial segment tree. By the way, can somebody send me the original array again on chat? Okay, thank you, Rishit. um, 3 2 4 1 5 5 2 6. Okay, so um, I'm basically doing max segment tree. So this is going to be the max of the two children. This is also going to be the max of the two children, and I'm always going the parent is always going to be the max of the two children that it has. Right. So this is how my max segment is going to look like. And now, whenever I want, let's say I query the first four, right? So if I query four, what I can say is I can binary search. I can say, all right, let's first query from 1 to 4, this segment. Okay. Does this, what is the maximum value here? It is 4, right? So the maximum value is 4. Is it greater than equal to whatever I'm interested in? Because if it is greater than equal to whatever I'm interested in, like here I'm interested in 4, it is greater than equal to 4. What happens is I can say my minimum index is going to exist in in one of these places. That is what I can say, right? So then once I do that, I will reduce my search space to this range, the red marked range, and then I will then query from 1 to 2. I will query what is the maximum value from 1 to 2, and I will be like, oh, it is only 3, right? It is 3. So actually, my minimum index is not going to be in this range. And when that happens, I can then instead go and query. I can actually go and reduce my search space to this. So this is my new search space, and inside this I'll again bisect this in half. I will then query the left half. I will be like, okay, is the value from here, like you can do 1 2 3 itself. You can query the 1 2 3 maximum value, and it will return 4. 4 is the maximum value, and then you can again be like, okay, is this greater than equal to 4 or not? And it is. So then your search space will reduce to this, and it is the only element that it is reduced to, right? Like you can basically pinpoint your location as 4. So that is how you get your minimum value. So did that make sense? So you get the position where you need to update, and then you just perform the update on that. You print the index of this and you also update that. So hopefully that made sense. And perhaps the way you can get the index is by also maybe storing not only the maximum, you also store the index of the maximum. So in the node, you store both maximum and you store the index of the maximum, right? So your unite is going to look like node L, node R, right? Node answer dot actually no, one second, you know the index because of the binary search already, right? So you don't need the index, actually, my bad. But yeah, you can just update the index over here, and then you will get uh the first position where the first number which is going to be greater than equal to it, and then you can do it. Now this the time complexity for this is actually going to become order of log squared. And the reason for that is you're performing your binary search is order log n, and then every binary search you're doing one query, right? And the segment tree queries order log n as well, right? So it's going to become order log n times log n, which is order log squared n, right? This is the time complexity for it. And does the time complexity make sense to everyone? The time complexity of this binary search plus the segment tree. Yeah. So although this is fine, this will pass. I think if you implement this, this should hopefully pass. You can do even better. You can do this in order log n. And the way you can do this in order log n is by internally binary searching inside the segment. Okay. And this technique of binary searching inside the segment tree is what people call walk on segment. Okay. So you essentially start at the current node over here. All right. And you say, okay, you also get a query. The query first, like let's say query was 4 that we got in the example. I check whether my left child, what is the maximum value in my left child? Now my left child's maximum value is 4. So this means whatever value I'm interested in, because 4 is greater than equal to whatever my query q was, q is equal to 4 here, I can say my first index is going to be lying in my left child's subtree, right? So I can just directly go to my left child over here. And then I again do the same check. I check, okay, is my left child 3 in this case? I'm currently at 4 now. Right? I'm currently at this node here. I check if my left child, which is this value greater than equal to my query q, which is 4? And the answer is no. And that means that the first index is not going to be lying inside the subtree of my left child. And if it is not lying in the subtree of my left child, well, it should be lying in my right child. So you go to the right child. Okay. And now you again check. You check, okay, is my left child's value greater than equal to the given query value, which is 4? Yes, it is greater than equal to. So then you go to the left child. And when you reach leaf, that is the node that you reached. That is the correct node that you reached, right? So you essentially figure out what node is the first node which is greater than equal to this query value using this binary search and segment tree. You're essentially doing binary search because your left child and right child, their ranges are halving, right? So that's what you're doing. And this is going to now work in order log n, because per node you're doing order 1 comparison between left child and query value, and you are then going down once each time after doing an order 1 comparison. And since you can only go down in order log n amount of times before reaching a leaf, your overall time complexity is going to be only order log n, right? So did that make sense to everyone? Aditya said yes, Nishant said yes. Other people? Okay. Cool. So this is going to be order log n, and this goes by again many names. This goes by walk on side tree. This particular thing where we find the first element is called find first, right? By some people. I can similarly ask you to find me the last index such that it is greater than equal to this or not. So that's going to become find last. Okay. So yeah, so you can call this by different names, but that's what it is. And uh, so if this value, like for instance the query 7, if this exceeds the root value, which is the maximum value, right? Whatever is the value of the root, that is the maximum value. So if this exceeds the root value, then you can say that the first index doesn't exist. So you can immediately print 0 in that case. Okay, so that was just some small detail over there. But otherwise, this is how you solve this problem, right? So I hope that made sense. Is everything clear to everyone? Okay, cool. So I think we can call it a day over here. It's already 7 o'clock. There's a code forces contest in like I think another hour. So that should be it. Can we continue till 8? All right. If you want to do one more problem, by the way, whatever I wanted to teach, the main parts have already been taught. Yes, especially the P4 and P5. So P5 is slightly more advanced, by the way. P5 will require certain more knowledge about a thing called DSU, disjoint set union, or people from a certain community like to call it union find data structure, UFDS. And although I might be belonging to that community, I would prefer to call it DSU for again certain reasons. But anyway, so you would require the knowledge of DSU for this. But so like you can try this out as well. I will also link the solutions to this in case I'm not able to describe the solution in this lecture. But we can discuss P4 right now. We can do that. And by the way, for people who wish to leave, you can leave. That is fine. The main part that I wanted to discuss, mainly being that each node can hold more than a single piece of information. Yeah, thank you, Pranav. So yeah, so the main information that I wanted to really talk about was that each node can hold more than just a single piece of information, and each and also like the walk on segment tree, the binary search inside the segment tree. Those were the two important topics that you need to really know. But apart from that, this is all you really need to solve segment tree problems, segment tree specific problems that you will usually encounter in most of the 99% of the problems you'll encounter this kind of segment tree. So the next two problems are some problems which make use of the structure of segment tree, right? And that is a really cool kind of aspect. But this is not really going to appear very often. Very rarely this is going to occur. So yeah, whatever I wanted to teach so far has been taught. So in case you want to leave right now, that is completely fine as well. Okay. So people who are going to are sticking right now, you can read the next problem, which is legacy, code forces legacy. One of my favorite problems on code forces. So yeah. And again, give you guys a minute to read this. Once you're done reading, by the way, please let me know on the chat so that I can continue the explanation of the solution. Um, Finished reading, Samvar and everyone else.
Yeah, 1 minute. I'm still just going through. Just 1 minute.
Okay, sure, sure.
Okay, yeah, I get the question.
Okay. Other people, did you guys read as well? Aditya, Yaman, Lander, Rishit, Avigna. Okay, Aditya said yes. Avigna said yes. Cool. So if everybody read the problem, then let's go back to OneNote. Um, okay, cool. So the problem essentially is saying that we can add three different types of edges, right? The first type of edge is between directly from V to U. Okay. The second type of edge is between all nodes from V to all nodes from L to R. The second type of edge that you can add. And the final type of query that you can do, that you can perform, is L to R to all the nodes of V. Okay. Now, there exist solutions that can do this in order log n log n. Okay, there exist solutions that can do this in order n log n. But uh, I'm not really going to talk about that solution. We are going to talk about a solution, a much cleaner, like not cleaner, I would say, a very cute solution involving segment trees. And that's going to work in order n log square n. Okay. Now the way you can use segment trees is uh, there is actually, you should be aware of one very common trick that you can use in graph problems, and that is the idea to have dummy nodes. Okay, nodes that you create to make the life simpler, in the sense that you can reduce either the number of edges, number of nodes, something. In order to reduce those, you create dummy nodes that aid you by like reducing one number. In this case, it's going to be reducing the number of edges, because the number of edges can go to like order n q. I'm just going to write n square over here, but yeah. So number of edges can be huge, and the idea of dummy nodes will help us reduce this order n square number of edges to something cleaner, something better. Okay, and how do we create dummy nodes, you might say now? Now this is where segment tree comes in. So I will like, let's not worry about the third type of operation. Third type of operation is going to be very similar to what the second type of operation is going to become. So I will only discuss, and the first type of operation is obviously very simple. You can just do g of b dot pushback. You can just directly do that. You can just directly add an edge. So the first is not very complicated. It is not hard to understand. It is quite simple. The second is mainly what I'm interested in. And if I can perform the second, you will be able to perform the third type of operation as well. Okay. So the way we do the second type of operation is, consider a segment tree. I'll again paste my original segment tree over here. Okay. So let's say I have 8 nodes, and my nodes are like this. Okay. So this is my node 1, node 2, node 3, 4, 5, 6, 7, 8. Okay. What I can do is, I want to add an edge from B to L to R. This is the kind of operation that I'm trying to perform. What I can do is I can direct all these. So all these segment tree nodes, by the way, are going to be now part of my graph. Okay. So all these nodes are going to be part of my graph. These are all dummy nodes that are acting as dummy nodes. And I will direct all these edges, parent to children edges, downwards. Okay. And I'll direct them downwards with edge weight 0. Edge weight is 0. All of these are 0. I'm not going to write down 0 for everything, but all of these are 0. Now, whenever you get a operation like add an edge from, let's say I say add an edge from node 1 to all the nodes from, let's just say, 4, maybe 4 to 8, no, not 4 to 8, let's take 4 to 7. Okay, with some certain weight w. Okay, what I can do is, I can add from 1 to, okay, I'll firstly split this 4 to 7 range into multiple smaller ranges that are segment tree ranges, like normally what a segment tree does. So it's going to become this 4 to 4, 5 to 6, and 7 to 7. Right? These are the 3 nodes that it segment tree. Whenever you query 4 to 7, it will get split into these 4 ranges, right? And these are what will return first. That's what I mean by splitting. And by the way, a very important property of segment tree is that it splits any range into log n ranges that you already, log n segment tree ranges. You can split any range L to R into log n segment tree ranges. So in this case, it split it into 3 segment tree ranges, right? What you now do is you add an edge from, I'll use ping for this, add an edge from 1 to each of these segments. So from 1 to this, from 1 to this, and from 1 to let's just from here, this. Okay, and each of these is going to be a cost w. And also another thing, each of these nodes are going to be having an edge with cost 0. Okay. But I'm not going to mention it. So now when you do this, if you try and query the distance between 1 and let's say like 5, what you can do is you can take this edge with weight w over here, okay, and you can take this edge with weight 0, and you can take this edge with weight 0. So you have a path from 1 to 5 with cost w. This is what you wanted. So does that make sense, people? Sambar and others, please. Okay. So okay. So one important uh, part about segment trees is that it can split any L comma R range into log n uh, disjoint segment tree ranges. Okay, so essentially what it can do is it can make a list of these segment tree ranges L1 R1, L2 R2, and dot 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 up till LK RK, where K is the number of ranges and K is going to be around log n. Okay, like it's going to be left like around order log n. It can split it into these ranges such that L1 such that R1 less than R1 less than L2 less than R2, so 1 less than R1 less than equal to over here, less than equals to, less than L3 less than equals to R3 less than L4 less than equals to R4 dot 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 up till K. So less than, so Rk minus 1 less than Lk less equals Rk, something like this, and the union of all of these segments together is going to be L. Okay, so more precisely, Li is going to be Ri minus 1 plus 1. This is what it's going to become more precisely. But anyway, this is what segment tree can do. It can break any range LR into log n disjoint segments, segment like which are already like which are all of these ranges, these log n, sorry, not n log n, 2n ones, 1 minus 1 ones. Okay, and that is what we are doing here. We are splitting this LR range 4 7 in this case into its log n constituent segments. So 4 7 got split into 4 comma 4, 5 comma 6, and 7 comma 7. Okay, this is what I split 4 comma 7 into, and the number of these split ranges is going to be only log n. Okay, and now what I can do is I can add an edge from the v node, whatever this v node was. In this case I took 1, so I can add an edge from 1 to each of these nodes independently. So like each of these nodes, which is 4 4. So 4 4 is represented by this, right? This node is 4 4. 5 6 as well. This is 5 6. Okay, and 7 7 as well. So this is 7 7, right? This all the red nodes are there. The red nodes over here. Okay, so I can do that, and each of these nodes has a path from them to the original node at like its subset node, subtree node, like leaf 5 in this case. It has a path from here to here with cost 0, right? So essentially what you can say is that the path, I have now created a path from 1 to 5 indirectly with weight w, and I've also done that for all other things. For 6 as well it is weight w, for 7 as well it is weight w, and for 4 as well it is weight w. So instead of adding for all of these 4 independently, I just split it into the log n ranges, constituent ranges, and added the edges to those. So does that make sense, Aditya? Okay, so um, that is the main idea of segment tree over here. You do this, and for the third type of operation over here, what you can do is you can have another segment tree. Okay, we'll have another segment tree like this, but in the next other segment tree, you're going to have edges directed from child to parent, so the opposite direction in the other segment tree. And then you will be able to perform this sort of operation, you know? And you can try figuring out how exactly you do this on your own now that you know how to do v to lr. Okay, and once you're so by the way, for each of these queries, you're only adding, because they're only log n segments, you're only going to be adding order log n edges. Over here as well, you're only going to be adding order log n edges. So overall, you're going to be having n log n or q log n to be fair, but like I'm just using n and q interchangeably. So n log n total edges in your tree, and then you perform Dijkstra over here on this graph to get the shortest path from one node to other. And the Dijkstra is going to have another additional log complexity, so it's going to become n log square n. So did that make sense to everyone? Okay, Aditya said yes.
Yeah,
And
that makes sense.
yeah, so this is a very cute solution where you are essentially using the L2R gets broken into log n segments property, and yeah, it's a very beautiful solution that way. So yeah, that was legacy. Uh, but yeah. So hope that made sense to everyone. Mm, this problem is slightly more advanced, but I can try explaining this as well if you. Okay, let's hopefully. Okay, I'll try wrapping this by 7:30. Worst case 7:40. But let's try this out. So I hope the legacy problem made sense to everyone. And Dijkstra has already been taught in the previous lecture by our very own Sambar Shah. So yeah, it was you who taught Dijkstra, right? Yeah. Okay. So yeah, you can then do Dijkstra, and this should solve the problem. Uh, all right, last problem for today: dynamic connectivity. As I said before, this requires the knowledge of DSU. But I will give you guys a minute or two to read before we move on to this problem. Discussion of the problem. I will briefly explain what operations we require for a DSU. I will explain what all operations a DSU can perform, but I will not be going into the details of what a DSU can do.
So this is just if there are no updates, this is just normal DSC, right?
Sorry.
This is just DSC with updates. Right? The updates are the only like
Yes. So
yes.
this is DSU with updates. Yes, this is what it is. We need to figure out how to remove edges. And DSU can't properly do that. It can't handle that. So yeah, this is essentially DSU with updates. Yeah, right. Okay, so I'll assume everybody read the problem. Did everybody read the problem? Rishit, Yemen Lander, everybody. Yeah. All right. Excellent. So the solution now, I will go back to OneNote is going to be, okay, so we have two types of operations. Actually, before that I'll explain what a DSU should be able to do. So this is actually called a DSU with rollback. Okay, now what a DSU with rollback can do is it can perform two kinds of operations. It can do add edge. Okay, it can also do count components. Okay, it can do this operation as well. And one more thing that it can also do, this is the additional thing, which is it can delete the last edge that it added. Delete the last edge that it added. Okay, are you aware of this, by the way? This operation, Samba?
I was actually aware of like the first two mainly.
Okay, all right. So anyway, this is called DSU with rollback. And usually DSU, if you just have only these two types of operations, it is usually or inverse Ackermann function, order alpha. But with this kind of operation, with this operation as well, we can perform these two in, we can perform this in order log n, add, 1 second. You can perform, yeah, add edge is going to be log n, count components is going to become order 1, and delete the last edge that is added is going to become order 1 as well, I think. Yeah, you should be able to do order 1. So, but yeah, so this is what is the time complexity for each of these operations. And for those who don't know what DSU does, what DSU is, assume that we can perform these three kinds of operations already. Okay, like assume we have a data structure that can perform these three operations. Okay, make sense to everyone so far? By the way, delete the last edge that it added. We can do it in a way that, like, we can say add a new edge, add a new edge, add a new edge, delete edge, add a new edge, delete edge, and go back like this. So we can, so once we delete the last edge that we added, the edge that we added before that, that becomes the new last edge. Okay, so we can perform this like a multiple times continuously, this operation. Okay, that's what I wanted to say. All right. So now what we do is, now here the geniosity part. Uh, we create a segment tree on the queries. Okay. So what is going to happen is each edge, right? Each edge is of the form a comma b, right? This edge is going to be in the graph from some query L to some query R, right? Like it's the active period for that edge, right? So you add it at some moment R, sorry, some moment L, and then you delete it from the graph or whatever at time R, right? This is what you're doing for each edge AB. Yeah, makes sense. So each edge AB has a corresponding LR period, which is the time that it got added to time it got destroyed. So this is the active period for that edge. Um, does it make sense? Samva, Aditya, Rishit, Yemen Lander. Okay, all right, cool. So yes, so this is what we do. And now if we have this L to R period for every edge, by the way, for an edge that doesn't get deleted, assume that it is from like L to infinity or L to some query number of queries plus like 5 or something, right? Like assume it is till infinity, whatever, you can define your infinity in the code. Okay. So now what we do is we maintain the segment tree on the queries. So when I say that, I mean on the query timeline. So actually let's just take this again, segment tree that we initially had. Oops. Okay. So I'll just actually keep it here. Okay. So okay. So what we do is I can, so let's say I have 8 queries totally. I say add edge 1 2, add edge 2 3, add edge 3 1, remove edge 1 2, add edge 1 4, remove edge 2 3, add edge 4 3, and remove edge 4 3, something like this. Or let's say remove edge 4 1 if you want. Okay, so we have 8 queries totally. Now for each thing, what I'll do is I'll keep track of what is the timeline for each edge. So we have actually, how many edges do we have? We had 1 2 edge, we had 2 3 edge, we had 3 1 edge, 1 2 got deleted, then we had 1 4 edge, then we had 2 3 which got deleted, then we have 4 3 edge, then we have 1 4 which got deleted. Okay. So timeline is what I'll do it now. So this existed from time 1 to time 4. This existed from time, actually this existed from time, yeah, time 1 to time 3, right? Because at time 4 it got deleted. So time 1 to time 3. This existed from time 2 to when did it get deleted? Over here. So that's like 6, I think 6, 7, yeah, 6. 3 1 is from time 3 to, okay, it survived the entire thing, so let's say 8. And next is 1 4 which got added at time 5 and got deleted at time 7. So like it's the existing period, so 5 to 7 is where it exists. And 4 3 got added at time 7 and it never got deleted, so 8. Okay, so sorry for taking up time there, but okay, so now does the whatever I wrote here, does that make sense over here? All right, so now what I can do is I can, so each node is now going to hold a list of edges. Okay, it's going to be a vector of edges. So each node is going to be a vector of edges. Okay, more precisely, I can break this 1 to 3 range, right? This 1 to 3 range, I will break it into um, its constituent, like what do you call, ranges in the segment tree. So this is 1 to 1 2 3 4 5 6 7 and 8, right? So 1 2 will get added to the nodes 1 2 and 3. Okay, so over here I add 1 2 edge, and over here 3 as well gets added 1 2 edge over here. Okay, I'll probably run out of space, but I will try to squeeze stuff in. 2 to 6. Okay, so 2 is going to become 2 3 edge is going to be at 2. Okay, and at 6, right? Or that's it's over there. So 6 is going to be over here. So 2 3 is also going to be here. 2 3 is also going to be here. Next is from 3 to 8. So 1 3 edge, 1 3 edge is going to be here as well. Next is from 1 to 4, which is 5 7. So 5 7 is from 1 to 4 edge. Sorry, not 5 7. I messed up. So from time 5 to time 7, it is going to be 1 to 4. So time 5 to time 7, it's going to become 1 4 also. Okay, so over here we also have 1 4 edge over here, and at time 7 I also have 1 4 edge. Finally 7 8 is 4 3. All right, phew. Okay, I think I did the segment tree. This 1 4 edge is a part of this node itself, by the way. Okay, cool. So this is what my segment tree is going to look like. Now what I do is I essentially say that at any time at 3, whatever edges are going to be on the path from the root to this, right? Those are the only edges which are going to be on at that particular time. Does that make sense to people? So at time 3, I can say at after this query, okay, after this at this time, I can say that only the edges 2, 3 and 1, 2 are going to be there. Which is 1 second, which seems slightly wrong. Is it correct? 1 second, what happened to 3, 1? Oh, 3, 1 is from 3 to 8. I see, I see. So I did mix up. So 3, 1 and so 3, 1 is also going to be here. 3, 1. So on the path from the root to this, okay, whatever edges are going to be there, those are the edges that are on at this particular time. That is what I'm going to say. So in this case, at time 3, I can say the edges that are on are like nodes 1, 2, and 3. Let's assume they're like this. I can say you have 1, 2 edge, you have 2, 3 edge, and you have 3, 1 edge. So this is what the graph is going to look like at time, and you also have 4 over here, at time 3. These are the whatever edges were on the path from the root to node 3, those are the edges which are going to be on. Does that make sense to everyone? Samvar, Yemen, Aditya, Rishit again. All right, okay. Cool. So what I can now do is let's come to 1. Okay, so the way I come to 1, like node 1 is this, right? Actually, I'll also number the segment trees using my numbering. Okay, so let's come from the root to node 3. Okay, so the way I do that is I come from here, I go here, I go here. When I come to node 2, I will add the edge 1, 2. So I will say, please add edge using the operation that I had over here that I mentioned. Right? Where did I mention? Yeah, you can add edge. This operation I will use, and I will add an edge 1, 2 in the segment, like in our data structure. Sorry, right? In our DSU. And then I go to this. Okay, and I'm like, okay, how many components are there? Then I'll use my components thing. All right. And I answer my whatever answer I got, I will answer that at this moment. I got my answer at 1. Okay. After that, what I will do is I will go back over here and I will go to time 2 now. Okay, which is node 4. And now I need to obviously add 2, 3 edge as well. And once I add 2, 3 edge to my data structure, I will then have my answer for 2 available. Okay. And now I need to go back. Now going back is just a rollback, right? Going back is now rollback. So now roll back the last edge I added, which is 2, 3. Now I need to go back again. So I'll again go back, which is now going to be deleting the node 1, the edge 1, 2. Okay. And now I'll go on this side. Now I add 2, 3, 3, 1 edges. Okay. And I go here, which is the next in line. And I will now also add 1, 2 edge. And I can again answer how many components are there. So answer of 3. Right. And then I can again roll back. And that is going to be deleting the last edge that I added, which is 1, 2. And then I go here. I answer whatever I got the answer here. And then I again delete whatever this edge. In case this had any edges, then I would have deleted those. But it doesn't have any edges. Now I need to go back again. So I roll back in the order that I added these. I'll reverse roll back those in the reverse order, right? And now I can go back. I can go back. And I will now go from here to here, from here to here, and from here to here. Then I will be able to answer for node 10 time 5, right? Then I can roll back. Then I go to time like node 11. I can answer for time 6. Again, roll back, come here, go there, and answer for node 13 times 7, roll back, come here, answer for node 14 times 8, roll back, roll back, roll back. Oops, roll back, yeah. So that's how I do this. Does that make sense to everyone? So this is like a very beautiful solution as well, because we not only use the idea about breaking each edge into log n segments, right? And by the way, this is why it works, because the overall space complexity for this is going to be order n for the segment tree, order n nodes for segment tree, plus there are order, if there are like total q edges that you added, then they're going to become q log n edges as well. Okay, this is the space-time complexity. And because of your DSU with adding edges being log n, right, your overall time complexity is going to be like q log squared n. So this is going to be overall time complexity. And yeah, that is how you solve this. I hope that made sense to everyone.
Yeah, that made, like, I got the basic idea, I think.
Yeah. So
It's a pretty neat solution.
yeah, this is a very, very beautiful solution, because you're using, firstly, you're using the fact that this is a tree, right? You're doing the pre-order traversal in some sense of this, yeah. And you're using rollback operations on DSU. You're using the log n segments idea as well. It's a very, very cute problem. All right, well, if everybody understood, then that is it for today. That was the segmented lecture. The last two problems were slightly more advanced, but hopefully you guys understood that as well. What is a lazy segment tree? Lazy segment tree is like, we updated a single value, if I remember, right? Yaman Lander. We updated a single value. Um, and in segment tree, sorry, in a lazy segment tree, you update a range of values. So we are going to have a range update as well. And that is the only difference between segment tree and a normal segment tree, a lazy segment tree and a normal segment tree. But the range update was not covered in this, because that will require lazy segment tree. We will need to do a little more stuff as well. Update will become slightly more complicated, but yeah. Otherwise, the main idea of segment tree was this, and I hope everybody understood that. Yeah. All right then. That was it for today. Good luck with the code forces contest in case you're giving. And with that, I'll stop the recording and end the meet. Are there any questions?